Okay, so welcome everyone to Machine Learning Paper Club organized by NPlan. This week, Arvid is going to be leading the discussion, and it's a bit of a deviation from what we usually do. It's not exactly machine learning, but it's still a very interesting paper. Go for it, Arvid.
Thank you. Try to share screen. Can you all see that? Good. So yes, hello everyone. Thank you very much for joining. My name is Arvid. I work with DraftKings. I have some of my colleagues actually joining in today. Please feel free to ask questions at any point. I might be going too fast. Some of the concepts here might be not exactly straightforward. And so if we have a discussion, it makes it easier for everyone, including myself. I got to this paper by chance, actually. I was looking for something about sequence analysis. We have at work a problem where we have symbolic time series, essentially long series of numbers, and we wanted to see whether there are some patterns in there. And I got to this paper, and I remember the author from many years ago. I looked at another one of his papers, and it was actually really good. And so I digged a bit deeper, and he was saying that this idea, this matrix profile, is the best idea in time series of the decade. Now, that is certainly a very large claim, and I don't know whether it's the best idea, but I think it's certainly a very good idea and something that can come in handy in a lot of different applications. So I'm going to talk first about what this matrix profile is. Then I'm going to talk about what are some applications of it. And then at the very end, I'm going to talk about how it is actually being calculated somewhat efficiently so that it's actually usable for the different applications. Like I said before, at any point in time, please interrupt if you have questions. So what is the ultimate problem? So the basic problem that this paper is attempting to solve is called the similarity join. The idea is you have a collection of data objects, and you would like to know what is the nearest neighbor of each object of your collection. And that seems very abstract, but actually has very many applications. In this particular instance, they're talking about time series, where the data objects are subsets of time series. And if you can calculate this, you can actually solve many real-life problems. You can think of, for example, DNA is a string, and these can essentially be mapped to a time series, or even two-dimensional patterns can be mapped into one-dimensional time series, and this whole thing applies. And it is something that is just very, very useful in a lot of actual practical applications. The cool thing is once you be able to solve this problem, the self-similarity join, you're actually solving many other problems as well. You can think about if you find that someone's nearest neighbor is very far away, then it means that this particular data point is not very well represented by the rest of the data points, so it's an outlier. So if you can solve this problem, you also can solve outlier analysis to some extent. You can find motifs, so these would be subsections of your data set that are very similar to each other, that are repeated, and these are often by themselves then interesting for other applications, say machine learning, where the motifs could be used as a feature input, for example. But generally, the problem is it's very expensive to calculate, right? At some point you have to measure the distance between each and every pair of your data set, and that is what's quite heavy to do. The paper starts with some definitions, and we probably should go through these in a bit more detail, just so we know what objects we're talking about. The basic idea is what's a time series is essentially a list of numbers, of real numbers of a certain length. The length of the time series here is always given as n. So if you see n, it means the absolute length of the time series. Then a subseries or subsequence is a part of that time series that starts at an index I and has a length m to it. And so m is our motif length that we want to use to check for typical size scales. So m generally will be a parameter in this algorithm. Like at the beginning, you have to choose what sort of width or window width you're interested in, but everything else will be parameter free. Then the next concept is the distance profile. That is already a bit more complicated. This is, so you have your series and you have one motif. Do we have actually, can I write on the screen somehow? Carlos?
If you look at the upper part where the green thing is, you should be able to see the options.
Yeah. It's there.
I think there's a tooltip there in more.
Yeah, got it. So what is the distance profile? The distance profile has a query, which is a subsequence. So in this case, it would be this thing here. And for time series, the distance profile is you take this query and slide it across the whole time series and calculate at each point what's the Euclidean distance between this query and the time series at that point. So for this particular query, you see that you get a timeline as well. So it's a sort of meta time series. Oops. And say at the starting point where the actual motif starts, oops, the distance between your query and the time series is 0, right? Because you are actually comparing the query to itself. So there's always, it's going to be a minimum at the point of the query itself. So this is called the exclusion zone because you want to exclude that window. But apart from that, you get for every point of your time series the comparison to that query. And there's a distance profile. So you see that at the beginning, this particular piece of the time series is relatively far away from that particular query. Whereas if you go closer to this formation here, you actually get a dip because this formation is sort of similar to that query. So you can see already where this could be quite handy. If you look at the distance profile, you can see interesting points immediately. Either they are very, very large. If a point is very large, it means that subsection is very different from the query. Or if the point is very, very small, or the distance profile is very, very low, it means that you find a point that is, or a subsequence that is very, very similar to that query. And the matrix profile, the next step is the generalization of this. Oops, sorry. Yeah, so it's also a time series. And the matrix profile is now a generalization of this distance profile. Distance profile is only for a single query. But now the matrix profile is the minimum of all the distance profiles for each subquery. What is that? So you have your data time series, and you have this matrix profile. Now this means that at any point here, it means that the closest distance that this subsequence has to anywhere else on the matrix on the time series, the minimum distance is this, right? So you see that points that have a very low distance to anything else, there must be somewhere along the time series another point that is very similar to it, right? Otherwise, points that have a very high minimum distance, they are very dissimilar to anything else is potentially on the time series. And so this matrix profile is a sort of aggregate object that tells you a lot about the properties. Was it clear? Should I repeat that?
I think it was clear.
Very good.
Yeah.
Then drawing and going to the next step are mutually exclusive. The last generalization or the last object we need is the index profile. So we have already the matrix profile, which is the smallest distance for each point of my time series, given a certain motif width. Now the matrix profile is an index that tells me for each point in the time series where is the next closest sequence. And of course we have the self-exclusion, so we don't trivially index back to ourselves, but rather it says, say at the 100th position of my time series, the matrix profile index would say that the closest motif is at the 200th position. So it's essentially a mapping between different sections of your time series. And once you have that, and typically you would want to calculate those things at the same time, because once you know which one is the minimum distance, you also know where you calculated from, so you would update them at the same time. So that is the basic idea of a matrix profile and the matrix profile index. You know the smallest distance at each point to all the rest of the time series. And typically this also can be done between time series. It doesn't have to be just one time series. That's maybe the most common way of self-searching for motifs, but you can also do it between time series, like finding for each subsequence of one time series, what is the closest subsequence on the other time series and how close is it? Now, what are some applications? One that I found really cool is this genome application. You can actually take your genome.
So can I make a question? Is there a reason why you compare to the first value in the time series rather than, for example, the maximum, the minimum, the average? So why the first? Is it just because it's the first one that will come in?
Sorry, what did you mean by first? You compare each sequence of the time series or each subsequence of the time series to every other subsequence of the time series, and then you take the minimum in distance. So you try to find the closest neighbor.
Yeah, but for the matrix profile, it says the vector of distance is PAB. So it is the shortest distance of each element in the first series to any other. Oh, okay. Sorry.
That was when you have more than one series. So you have two series, right? So series A, series B. You quote unquote merge them by doing that. That's why it's called the series join. It's not the first element of the series, but rather you have two series, you join them. I took some of the definitions out, and probably that kind of gets stuck in there.
Okay, it's good. Okay.
But it's find the subsequence on the other series that is closest to the one in the first series. Yeah. Now, in the genome application, so how can you make your genome, which is 4 base pairs, into a time series? What you can do is you can start at 0, and every time an adenosine comes up, you go up by 1. Cytosine comes up by 2, or for the other ones, you go down. And this way, you can take your DNA strand and turn it into a time series. And then you can run all sorts of analysis on that. That has been used, I think, in bioinformatics for quite some time now. And one application is you can look for interesting patterns in there. So here we have a piece of chimpanzee genome, I think. It's 1 million base pairs long, so quite a large one. It's in red. And in blue, you can see the matrix profile. So that is for each subsequence, what is the shortest one given a motif length? How long is the motif length here? In this case, it's 60,000. And you see, you get actually quite a rich structure in your matrix profile, meaning there are some points in there that are very small, meaning that there are sequences actually in there that seem to be repeated. And actually, if you zoom in the lower part of the picture, you can actually see such a sequence, and it's remarkable, right? So you have a subsequence of length 60,000 base pairs that is almost identical to another one that is a couple of 100,000 base pairs shifted to the right. And that likely points to some event in the genetic history where a particular piece of DNA got duplicated and re-merged into the genome and just left there. These things are called amplicon. Now, if you have a good way of calculating this matrix profile, you could find these, and you could find them for different motif bits. So that is certainly quite useful for genetic research into our evolutionary history, for example. Another thing is application I found quite interesting is finding differences in time series. So you have two time series where you would think they are basically identical. And here they have the example of an audio recording of Harry Potter. One is the UK version, one is the US version. They are the same book, but spoken by different people. And you can also do this series merge on them and find out. You would expect them to be very, very similar. So actually you're interested in what is the subsequence that is maximum dissimilar. And if you do this for I think here they have 1.6 second clips, you actually find, using the matrix profile, 2 sections where actually the word order between the UK version and the US version has slightly changed. So that is, of course, quite neat if you want to do this on large data sets. if you can reliably calculate this matrix profile, you can find those differences between a series that are different. The next one is outlier detection. I mentioned earlier, say for ECGs like this cardio, what are they called? Electrocardiogram. You can here they calculate the matrix profile, and you would expect that your heart rhythm is similar, so that pretty much at any point you can take the subsequence and you would find something more or less similar somewhere along the time series because your heart has that rhythm. However, if you find points like this one here, which are maximum in the profile, it means that there is something happening where there's nothing else there that is similar. So it's probably some sort of mistake that goes on in your heart. So here they found some arrhythmia, like where your heart pumps in a different way than it usually would be expected. And you can find these. Now, naturally, if you have many of those and they are similar, they actually go from becoming outliers to becoming motifs, because then you would find them along the line somewhere else. But either way, you have a way of identifying those events. And there are actually quite a couple of papers after this one. If you look at the title, it says Matrix Profile 1. They have, I think, 22 papers by now, and they actually make use of heart data and these matrix profiles to cluster these special outliers or special motifs into disease categories. So it's definitely quite interesting if someone wants to analyze such an ECG fast. Having access to this matrix profile makes it very easy. Another application which I really liked is music. Here they used two songs. One is by Vanilla Ice, Ice Ice Baby. You might have heard of it. The other one is Under Pressure by Queen and David Bowie. And if you look at they are called MFCC. I don't know what they stand for. It's like essentially one way where you can take audio recordings and turn it into a time series. And if you look at it, it is not immediately obvious that there are similarities between them. However, if you run the matrix profile on a motif width of 5 seconds and you look for what is the most similar subsequence, you will find this sequence, which looks very, very, very similar indeed. And now we tested it earlier. We don't have the audio recording. I actually have the pieces of the clips, but if you would listen to them, you would immediately hear where Vanilla Ice has actually stolen the baseline of Under Pressure. And I think at the very beginning he even started denying it, but it was very obvious that he did. So this plagiarism detection is one possible application of this matrix profiling. Another one is regime detection. That is where we actually make use of the index profile, right? If you remember, the index profile tells me for my time series which is the next closest one. So essentially, where's the location of that one? Now, if you have a time series like this, you can calculate the matrix profile, and then you can actually check for each. Let me see what I annotate that. So you can make a cut at the time series like this, and you can essentially check in which direction do the indices go. So for each time series, like point here, say the next closest index could be over there. So the mapping would be here, or next one might go over here. So you can essentially check at each point, if I were to draw a line, how many index references are crossing over the line. If you have a point where many lines are crossing over, it means you are well within one regime, because all the closest neighbors are somewhere across. However, if you find points where these splitting lines are minimal, then you know that, say, if I take a point to the right of it, it's more likely that their nearest neighbor in that distance space is also somewhere to the right, and points that are to the left of it, their nearest neighbor is also somewhere to the left. So points where there are very few crossings between the indices tend to point towards regime changes, where your time series has changed behavior. Yeah, and this can be, of course, then also measured automatically. And here, this is, I think, for some human behavior. I don't know whether they track motion or just some other time series quantity, and you can actually see that different activities quite well fall actually into different regimes that can be identified by the matrix profile. These are the basic applications that were covered in this paper. Are there questions at this point? No. Let me see drawings. Then the next step would be to explain how does it actually work. So that is nice. So we know having the matrix profile does indeed solve a lot of the problems. The problem we have now is actually calculating it and calculating it as efficiently as we possibly can. That is the hard part, really. Oh, still doesn't work. Yeah. So naive algorithms don't scale very well. I think that's no surprise. You would need a lot of space, right? So if you take all the subsequence of your time series and measure the distances, you fill out the matrix, and that matrix becomes very, very large. That's actually also where the name profile matrix comes from, distance profile matrix. And it becomes very, very cumbersome. That doesn't work very well. There are, of course, many attempts of doing that. People have noticed in the past that finding interesting subpatterns is useful for all sorts of applications. Many of these actually rely on some fine-tuning, that you already have to know a lot about the problem, about the problem space you're working on. And there are examples where they have 4 or more parameters to be tuning. And many authors would agree that, yes, it works for this very particular parameter combination, but it doesn't generalize. And of course, in practice, if you think of it from a machine learning point of view, that's a hard thing. It's a bad thing if you have to fine tune because you're essentially overfitting to the results of your training set, and you don't want that. It does not scale well with motif width typically. Most algorithms work well on small motifs because small motifs you can easily calculate distances. Doesn't work well once the motif width gets wider. Now, we saw already in the genetic example that motif widths of up to several thousand, like in that case, I think it was 60,000, is also very useful for genetic analysis. So we need sometimes thousands, maybe even millions of base pairs as a motif. So we do not want something that only works on very, very small scales. There are also applications that work approximately, and these are often you often have false positives or false negatives, which depending on the application can be something that you don't want. So what are some of the insights the authors used in order to make this problem digestible? They said that, of course, you're only interested in the minimum of the distance profile. So at each point in time, you essentially only have to store the one-dimensional profile. You don't have to ever really expand it into a matrix, because once you know a point and its distance, shortest distance you currently know, if you find another point that is even shorter or even closer, you would just replace the minimum distance and you replace that point. So space-wise, there's never need to actually expand the whole thing. So yeah, that's that. Distance profiles you can compute in parallel, right? Because it's map reducible. So if you have 10 distance profiles, you can combine them and still take the point-wise minimum, and you still converge to the truest of values. One other thing is that you're often interested actually in the normalized distances. So if you have 2 time series that are shifted in the y direction, you can still compare time series by essentially taking the means out and removing the variance, and then you still can compare them, and that works rather well in practice. Now, I think the biggest insight one of the authors of the paper had that was that you can actually there's an equivalent problem there. You can calculate the distance between two subsequence, or you can use instead the scalar product of two subsequences. So here you have Qt is a scalar product of the Q is a query, T is or Ti is the time series interval. If you take the scalar product, you pretty much get the distance for free, because it's literally just a formula that translates one to the other. And meaning that rather than trying to work out how to calculate the distance effectively, you should try to work out whether you can calculate the scalar product efficiently. And if you can do that, then the distance comes almost for free. And the scalar product, turns out, can be actually calculated fairly efficiently. Now, how do they do it? They use a sliding dot product. So you take the time series and add zeros at the end. So you essentially double the length. And then you take your query, you reverse it, and add as many zeros as you need in order to get to the same length as the original time series. So now you have two queries, or two series, TA and QA. Each of them you fast Fourier transform, and fast Fourier transform is an algorithm that is very well known. It is practically very well optimized because it is so common. So people have put a lot of effort in to make it run fast. So you can do that fast. Then you multiply it pointwise, and then you inverse transform, and then you have the sliding dot product. And sliding dot product means you have, when you've done this, you have calculated dot product at each point of your time series with respect to the original query Q. So you have calculated, yeah.
I was just going to say that this is super clever.
I think so, yes.
Because you're creating the two time series that you need, and then you're doing a fast convolution on them.
Correctly.
And then it's like, there you go, you got your sliding dot product.
Exactly. So rather than calculating distance by distance, you calculate your query distance to everything at once in this fast Fourier transform. And there is actually, that is not in this paper, there's actually another paper, there's even one more trick you can do by, actually I probably should talk to this towards more towards the end, because this is the whole, so we have a single query of your time series, and now we have calculated the sliding dot product for the whole time series. So we know the distance profile. And once we have that, we know how to calculate the matrix profile, and that is what's the mass algorithm. The Moines is one of the co-authors, similarity search. So you take a single query, you calculate the sliding dot product, so you have the distance profile, from that you calculate the standard deviations, and from that you have the distance profile. Now you have a very efficient way of calculating the distance profile for one time series. And now comes a stamp, it's called. I don't actually know what it stands for, but you take this distance profile of one query, and you choose whichever query you want from your time series, calculate the distance profile, and update some index you already have. So by just taking the minimum, and then you just do it over and over again by choosing another query, calculate the distance profile, take the minimum, update the indexes if you need, and you have it done. And it still runs in square time, or n square log n. But because this fast Fourier transform is very well optimized, in practice it's almost more like n square. And the important thing is also that you need only linear space requirements. Why is it important? It means that in the future you can actually put it also onto a GPU. Even larger sequences do fit onto a GPU. And in future papers, they actually make one more trick, where rather than choosing randomly which query you want to calculate the next distance profile and update it, you can see that if you have queries that are actually very close to each other, say only by one shifted off, you can actually update your distance profile on each index much faster by just using that. The Fourier transform are also very similar, so you can even make it n square rather than n squared log n. And Well, in this paper, they say, oh, yeah, this log n is not important. In the next paper, where they actually get rid of it, they say, oh, it's really, really important, really speeds things up a lot. So naturally, you have to take these things with a grain of salt. But there are no tunable parameters. You only put in as input your length m. And that really comes to the queries you sample from your time series. And what is also really cool, it's independent of the query length, right? Because you always add up to the bits of your time series by putting the zeros on it. It becomes independent of the length of the motif, and it scales very well. So here's actually against one of the other algorithms, which when they came out with this was already considered to be a really good one, the MK algorithm. And you see A, it runs faster, and B, it runs faster even if you change the query length, the speed doesn't change. There are cases where it's even a bit faster when you make it longer, just because the fast Fourier transform works well if the m is certain powers of 2. So that is really, really cool. Yeah, they check it. It's good. So naturally, it still costs quite a long time to calculate these. So for 2 to the 21, it takes 4.2 days. And that is their first implementation. That is about, I think, 2 million, or a length of 2 million of your time series. In future papers where they used GPU and some smart parallelizing, they essentially done like at least 100 million lengthwise time series in less time than that. So it definitely does scale to a point where genetic investigations become a possible thing. And the cool thing is also that you can, if you're really stuck for time, approximate it by just sampling randomly queries from your time series. You run the distance profile against, and if you sample randomly throughout, and because you know that if they are overlapping, they contain often similar information, you can actually get away by using a much smaller section or number of queries in order to get a good approximation. But in principle, the algorithm is of course exact. If you run it for all the queries you possibly can, you will get the exact answer. And what is nice for practical application is that it is interruptible, meaning you can stop it, the algorithm, and just later on start it again, start trying querying new, or start using new queries. And that is especially important when you have streaming data. Say you have your time series like this, as it is given there. And now assume you get more data coming in. All you need to do is take a new motif, calculate it against the rest of the time series, update your matrix profile, and you've essentially accounted for that. And this way it became, for the first time, actually possible to run this sort of motif finding on data problems that are long running and can produce data at a reasonable rate. So if it runs too fast, so if you produce data every couple of milliseconds, it probably won't work. But if you have like something like a oil rig or so that produces like a data point every 30 seconds or so, then you still can run the algorithm in real time and check for new patterns or new outliers in real time. That's obviously quite valuable. Now,
I have a bit of a question related to the motifs. So I imagine that the size of the motif, it is a bit of a hyperparameter in the sense that you want to, so you must know the time scale of the things that you're looking for, right? So for example, in the ECG example, your motif would be more or less the size of 1 beat.
Yeah.
So I guess in the limit where the motif, or to frame it as a question, is there a use case for where the motif is your entire sequence? Or for example, for ECG recordings, in public databases, they usually have like fixed size ECG. So you could eventually say, okay, my motif is the size of the entire recording.
In principle, but that sort of would trivialize the problem, right? If you know already your motif is the whole size, then you could probably just take the distance profile right away, right? Because there's literally no degree of freedom left to slide along anymore. Of course, in practice, that would perhaps not work so well when you say ECG, because the heartbeats might start like slightly shifted for each one. So you could get, say, if it's just roughly a sine wave, you just shift it by pi over 2, suddenly you are a cosine and sine are orthogonal, so the distance is 0, even though from your point of view it would still be more or less the exact same thing. But you're right. Motif width is an input parameter. It is also very much related to the question you ask, because you will find in many applications that different time scales have different behaviors you are interested in. In sciences, there might be, say in genetics, you could think of very small base pairs that essentially enfold structures within a protein. But then on a larger motif width, you're talking about chromosomal similarities that have been transformed. So this is a very different kind of questions you're asking there. But yeah, absolutely. Now, if you have a large time series, scanning through all the motifs is still going to be expensive. But,
yeah. I was also wondering about, so when they define the motifs, do they define them in numbers of samples, or do they define them in time scales?
What do you mean by number of samples?
Because I imagine that the size of your motif is going to depend on the sampling frequency, right?
Yeah, absolutely.
So,
they typically say when you have a time series at which frequency it has been sampled. So whether it's like a couple of megahertz or.
Yeah, I'm just wondering if there's a limitation on the sampling frequency of these time series. I know, like nowadays, it's hard to find a time series which is not oversampled, but I'm wondering if there's a limit where, you know, you simply don't have enough samples in your motif to get anything meaningful, or like everything will seem like it's similar, but it's an artifact of you not having enough samples in your sliding windows.
Yeah, I don't know, to be honest, but yeah, of course you can always choose the sliding window big enough so that it doesn't matter anymore. But of course, if you sample, it's a ratio of sampling rate to motif width that is probably your defining characteristic of this problem. The algorithm itself only works on the time series itself, right? It doesn't ask the question, where did the time series come from? Is the underlying process aliased or something like that?
Yeah, well, that's the thing, right? Like, if I guess the algorithm will work, but there has to be a limit where when the algorithm, maybe it tells you things, but those things are meaningless, right?
Yeah.
I was just wondering if they did that.
If the time series themselves are meaningless, there's, I think, not very much you can do unless you have some other reconstructive transformation that takes out this noise you added by something. Absolutely, yeah. I think there's one last slide I had. Yeah, so you can actually stream data, which is quite useful. And there's also in other applications, one of the nice applications is seismic data. So they actually found that there are motifs in earthquake data, and these motifs are often very far apart and yet look suspiciously very, very similar, because maybe the same underlying geological change has happened. And here they show that even by sampling a tiny fraction of all the possible queries you often get good indicators of what the ground truth values are, as long as these samples are reasonably spread. So here they have this 1% of the data, the possible query situations, you already get very good pointers of what your likely motifs are. So that is not a general truth, because that obviously depends on the time series in question you're looking at. But it has been proven quite useful, and they are, I think, collaborating with I don't know what you call them, seismologists, to to build systems that are real-time analysis of seismographic data, which is quite large data sets, quite generally, and quite complicated data set, because most of the time nothing happens, and only occasionally you have these interesting features. Yeah, that's it.
Yeah.
Right.
Yeah, I think it's really interesting. I have some doubts left about call it how you would deploy these kinds of things, because typically, and again, it goes back to the signals themselves, not to the algorithm, but like, because you would usually, if you're comparing data from different sources, it is very likely that they will be sampled at different frequencies. They will be sampled using different instruments, so that the amplitudes might be different. So
I would argue that is then where the choice of motif width is really crucial, right? So if, of course, if they are sampled at different speeds, wouldn't make sense. But you've seen in the earlier example of the Harry Potter series spoken with different narratives, right? So there are genuine differences in the series. It seems to be fairly robust to that. Why is it robust? Because of this Z normalization under the hood. That essentially the Z normalization only stretches, I think, in the Y direction. It doesn't stretch in the X direction. That is where then different sampling rates would essentially mean that you do it like that.
I guess so the Y direction is taken care of by the Z normalization. But still, it's quite fun. So could you link to the follow-up papers that you mentioned, so we can
I can put the website in there. They have there's actually it's called the Matrix Profile Foundation. It's essentially a group of people who really like those papers so much that they actually built their own Python a non-profit for it. They also have their own GitHub library. So, but there is Python code where you can just import it and run it, and you also have, I think, CUDA supported algorithms in there as well. So it's I haven't actually used it, but I want to. But it's supposed to be really, really straightforward. They were also at the last PyData. They gave a talk about this, so it's generally quite cool.
I have a question, Arvid. Yeah. I noticed that, for instance, in the genome comparison, essentially they flattened the 4 bases into one variable, so it's a single dimension. Is this method scalable for more dimensions, so time series that have more than one dimension? I'm thinking about, I don't know, electric signals where you have the real and imaginary component, and you also have the magnetic signal that usually goes along the electric signal.
It's a very good question, and there is actually a follow-up paper on that as well. Because you can imagine if you have, say, like a tracking device. I think they had the example of sports tracking. So if you go to like a sports analysis, what they do is they put, I think, these color dots everywhere around your body, and you would then do motion, be it like fighting, or be it some athletic exercise, and each of these dots essentially creates a time series. And if you track these, say for a particular motion, it can be that certain dots don't move at all, so there's literally no information in them, but others move in tandem. And so it can very well happen that you have a data set for each person of up to 40 time series, and then finding shared motifs becomes slightly non-trivial, right? Because then essentially the question becomes, what is a motif then? And here I think they generalized it to such a way that you choose another parameter k, and then you take the k nearest distances. So out of your 40, which one are the say 3 that are the closest? And so then by varying k, you can also do this fairly efficiently. You can also get a profile in the number of parameters you are comparing against, and it still works even if you have many more noise dimensions than signal dimensions, provided there's a signal.
Nice, thanks.
But I haven't read all their papers, but like I said, 22 is quite a large number, but they're generally of course, a bit derivative, right? Because it's a good idea, so they work with that, and they have, I don't know how many PhD students work on it, but generally cool stuff and really nice applications. Like they went out of their way to work with people in the field, industry, also on a variety of topics and sciences to find applications, and they found them. I think they did something. What was it? I think skull shapes of animals. For some reason, I don't know how it works. You can actually translate these into one-dimensional features and then map those as well, and you can see very interesting stuff there. Or yeah, I don't know, but there's a lot of really nice applications there. Yeah, that's it. Thank you very much. Are there any other questions?
Okay. Well, thank you very much, Arvid, for the great paper and the very interesting conversation about it. As usual, I would like to close by thanking everyone who's been here, reminding that this is a space for everyone to share their thoughts and the ideas that they have. And if you come across any interesting paper, you can just get in touch with us, and we'll be more than happy to accommodate for you, either you to lead the discussion or someone else to lead the discussion. And you can find all our contact information in nplan.io. So thank you, Arvid, again, and see you all next week.
Thank you, Arvid.
Bye-bye.
Thank you.